Section 2.7, Graphical Analysis of Velocity and Acceleration. So let's think of an example. A cyclist rides in one direction at a constant v, where v is velocity. And that can be graphically shown here on this graph of position, x, versus time on the horizontal scale, t. So we notice as time passes, right, 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, the position is also increasing. The cyclist goes from being at some initial position of 0 to 4 meters, to 8 meters, to 12 meters, to 16 meters, right? That's what this red line is showing. Now we could look at the change in position relative to the time, and we know that connects to our velocity, right? If you remember, we defined velocity on average is the change in position or change in displacement, delta x, all over delta t. So if we look at 2 points of interest as shown here, we could look at the change in position, which the change in position is 12 minus 4. That's going to be this 8 meters. So we have 8 meters, and then divide that by the change in time, right? Where we have 3 minus 1, that's going to be 2 seconds. And so this will then give us a velocity of 4 meters per second. Now, if you look at this delta x divided by delta t, you'll notice that that actually looks a lot like your rise over your run. When do you use rise over run? That pops up whenever you're talking about slope. So that's the flip side of this, right? That slope is equal to rise over run. So I'll put that first on the side because that's how I remember slope. Rise all over run. Rise is how much the graph has gone up vertically. Run is how much it's increased horizontally. So in this case, if it's a position versus time graph, the slope is going to be delta x all over delta t. Or in other words, that tells us that if it is a graph of position versus time, and assuming that you have a constant velocity, the slope will give you your velocity. So just knowing the slope of this graph tells you about how the cyclist is moving. So this shows a positive velocity, right? This is positive 4 meters per second. What if instead the line was flat? What would the slope be, or what is the slope of a flat line? Well, to think about that, we could look at a more lengthy example. I'll clear my pictures. Notice here in region 2, the line is flat. So what's the change in position? The position isn't changing, right? The cyclist might have stopped to repair a flat tire, or maybe just have a water and snack break, right? But either way, the delta x is now 0. Time is still passing, but the position is not changing. The cyclist is stationary. So if you look at the change in position over the change in time, you'd find that it's 0 divided by that time. So the cyclist is not moving. So when it's a flat line, that's 0 slope and 0 velocity. Similarly, you could have a line that is angled downward. In this case, the change in x is now negative, that the position at the end is lower than the position when it started. That tells you that the cyclist is headed in the opposite direction, right? If initially the cyclist was going to the right, now it's going to the left. So negative velocity is going to correspond to a negative slope, and thus the opposite direction. All right, so this is what happens if you have a graph, again, of position versus time. There's another type of graph that we can look at and use the slope to help us out. And that's a graph of if we have velocity versus time, right? Here, I'll get an even different color to highlight that this is different. Velocity versus time. Now we have our velocity at any given instant, right? Initially, the velocity is non-zero, that it starts out with 5 meters per second, like the coin toss, where the coin toss is moving upward. This is not like the coin toss in that this coin is not going to start slowing down and coming back, right? Notice the velocity just keeps increasing and increasing until after 5 seconds, it's nearly going 36 meters per second. So this is probably more like a race car. This is something that's moving fast. But once again, we can look at the change in the rise over the change in the run, or in other words, look at the slope, and that will tell us something. Here, if we look at the slope being equal to the rise over the run, which is delta V over delta T, delta V over delta T is not going to be equal to the velocity in this case, but this is equal to something else we've defined. This is our acceleration. So if you have a plot of velocity versus time, then the slope will give you your acceleration. So in this case, if we have a rise or change in velocity that's at positive 12 meters per second divided by 2 seconds, that would give you an acceleration that is 6 meters per second squared. So this highlights how you can use a graph to pull out some useful information. And you may see problems where they give you a graph as opposed to telling you the acceleration. You have to determine the acceleration from the graph, or determine the velocity from the position versus time graph. So this is just another technique that you can add to your toolbox in solving problems.